So we just looked at the alpha decay. In an alpha decay, a helium nucleus is released or emitted in an alpha decay. So helium, recall, has 4 nucleons, 2 protons. Atomic number is 2 and the mass number is 4. Also can be written this way. Now I mentioned in the previous video that the mass of the parent nucleus is greater than the mass of the alpha plus mass of the daughter nucleus. Let's take a look at one particular example here, uranium. It's a very unstable nucleus because it's very large. So you have 238 nucleons, 92 atomic number, undergoing an alpha decay. So 238 take away 4 is 234, and 92 take away 2 is 90. Looking it up on the periodic table, 90 gives you right here thorium. So we have thorium. Now, so this is the parent nucleus. Uranium is the parent nucleus. This is the alpha nucleus, and this is the daughter nucleus. That's just the name they're given. Just like in biology, when in a cell division you have a parent cell and you have a daughter cell. So this is a parent nucleus, and it has a greater mass than these two. So the sum is less than the total of the whole. Why is that? So what accounts for the missing mass? Where did that missing mass go? Why is it that you have less mass in the alpha and the daughter nucleus when it splits? The missing mass is actually the kinetic energy of the alpha particle and the daughter nucleus moving away from each other. So you could imagine that this is the uranium nucleus. It emits an alpha particle, and you have the daughter particle thorium, and as it splits up, it moves away from each other. So there's the conservation of momentum involved here as well. So let's take a look at the missing mass. So the missing mass can be calculated using Einstein's E equals mc squared. The mass of the uranium, you could actually look this up. I'm just going to write down the masses here for the sake of our concept. So it's 238.0508 atomic unit for the uranium, and the alpha is 4.0026 atomic unit, plus the daughter nucleus of thorium is 234.0436 atomic unit. So as you can see that this would be greater than that. So let's take a look at the missing mass here. The change in mass from the parent nucleus to the daughter nucleus. When you subtract these two, you get 0.0046 atomic unit. Now it's very small, but it is still less. So this is atomic units. We need to convert that into kilogram, the metric unit for mass. Recall that the mass of a proton and neutron, they are equal masses, is 1.66 times 10 to the negative 27. So 1.66 times 10 to the negative 27 kilogram per atomic unit, and that gives you 7.636 times 10 to the negative 30 kilograms. So this is the missing mass. Now let's take a look at the energy that the mass has been converted to. According to Einstein, this mass has been converted to pure energy. Also, it's vice versa. Energy can also create mass, and this is a groundbreaking idea from Einstein. So let's take a look at how much energy has been created from this mass as alpha decay happened. So mass is 7.636 times 10 to the negative 30 kilograms. Multiply that by celeritas, the speed of light, 3 times 10 to the power of 8 meters per second squared. And the energy produced is 6.8724 times 10 to the negative 13 joules. We're going to change this into electron volt. So multiply this by 1 electron volts over 1.6 times 10 to the negative 19 joules per electron volt. And you have changing this to mega electron volt, which is how it's usually expressed. This is going to give you 430 mega electron volts. So that is the amount of energy that has been converted from the missing mass. So it's not really a missing mass. It is accounted for in the form of energy released in an alpha decay. Now let's take a look at a beta decay. Right here. In a beta decay, so this is the second type of radioactive decay. There are two kinds of beta. You have a beta negative and a beta positive. So beta negative decay is it basically happens. This is 0, negative 1. This is how it's expressed. And beta negative decay happens when a neutron falls apart and changes into a proton and an electron. So it's pretty crazy that a neutron actually falls apart and breaks apart into a proton and an electron. It is important to note here that the electron that is produced here from neutron falling apart is a beta particle. This beta particle is not the same as an orbital electron. So a beta particle is an electron, but it's not the orbital electron that you have learned in your previous science courses. I'm going to just take a look at the typical Bohr model here. You have a proton with a positive charge and a neutron, which is a balanced number of positive and negative. And then you have, according to Bohr model, you have the electrons in the orbital shell. This is not the electron that we are talking about here in a beta particle. This is the electron that is found in the nucleus. That's pretty crazy because you've never probably heard this before, that electrons are found in the nucleus and not just what you have learned before in the orbital nucleus. So this is called the beta particle. Let's take a look at an example of a beta negative decay. So let's use calcium. Looking it up on the periodic table, you have 46 and 20. So calcium here is an alkaline earth. So calcium 20 and 40. I'm using an isotope of calcium, and very unstable, 46. So it's going to release a beta negative, undergoing a beta negative decay. And what happens is 46 take away 0, still 46, and 20. And this is a take away negative 1. So 20, negative 1, this will have to be 21. So looking up number 21 on the periodic table, and you get scandium. So scandium. Now, what happens in a beta decay is that a beta particle, as it is released, the electrons are assumed to travel quite fast, and an antineutrino is released. So this is an anti-neutrino, which is the antimatter of neutrino. So an antimatter has exactly the same charge, but exactly opposite spin. So this is what happens with calcium when it undergoes a beta negative decay. Let's do another example here. Let's try thorium 90 and 234. Again, look at thorium 90 on the periodic table, 90 right here, and 232 is what you have on the periodic table. So this is an isotope again. Something is happening with the neutrons. Okay, so thorium undergoes a beta negative decay. So you have 234 take away 0, still 234. 90 take away negative 1, so 90 plus 1. This is now 91. And you get protactinium. Protactinium and an emission of an antineutrino. Okay, let's do one more example of a beta negative decay. Let's try plutonium. 244, an isotope of plutonium, 94 nucleons, number of atomic number or protons, undergoes a beta negative decay. What you have is 244, 94 take away negative 1, so 94 plus 1, you get 95, and we have americium, named after America, and an emission of an antineutrino, so it's a V with the line at the top. So this is what happens in a beta negative decay. Now let's take a look at the opposite of a beta negative. So you have a beta positive decay. So a beta positive decay is also called B positive, and this is known as a positron. And a positron is an anti-electron. So this is the antimatter of electron, a pretty wild idea, the antimatter. So the anti-electron has the same mass of an electron, but the opposite charge. So it's called a positron. So let's take a look at a couple of examples of what happens in a beta positive decay. Let's look at potassium. So potassium is 19 on the periodic table and 39.1 on the periodic table for the nucleons. I'm gonna look at the isotope of potassium, 40. Okay, undergoes a beta positive decay. So 40 take away 0, still 40. 19 take away 1. It is 18, and number 18 is argon. It has become a noble gas, very stable. And what is produced here is a neutrino, not an antineutrino. So an antineutrino is the antimatter of neutrino. It's written as a V with the bar at the top. Neutrino is just a letter V. Let's do one more example of a beta positive decay. Let's look at calcium. On the periodic table is 20 and 40. I'm going to look at 46, isotope of calcium, okay, releasing a positron, beta positive decay. So 46 take away 0 is 46, 20 take away 1 is 19, and number 19 on the periodic table is potassium. And again, a neutrino is produced. So that is a decay. Now remember, a decay is an emission or a release. So it is found on the right side of the equation. It's if you're looking at a chemical equation in chemistry, it is a product as opposed to a reactant. One more thing I want to look at in terms of a beta decay is called an electron capture. So an electron capture is also known as the inverse beta decay. Now, capture means its electron is absorbed. So as opposed to released, it is absorbed. So in a chemical reaction, when you absorb something, it is in the reactant side of the equation. So let's look at examples of an electron capture. Let's look at calcium again. 20 and 46, just like what we used in the previous example. This time it is absorbing the electron. So electron, 0, -1. And what you get is 46 plus 0 is still 46. And 20 plus -1 is 20. Take away 1, which is 19. And you get potassium. And again, a release of neutrino as a product of an electron capture. To one more example of an electron capture, let's look at rubidium, 37 and 83, absorbing an electron, and what you get is 83 plus 0 is 83, 37 plus -1 is 36, and what you have, number 36, is krypton. So krypton plus a release of neutrino. So this is another way that a neutrino is released through the electron capture or inverse beta decay. It is exactly like a beta decay, except an electron is absorbed as opposed to released. The last radioactive decay that we're going to look at is a gamma decay. So what happens in a gamma decay? So gamma decay involves pure energy. It does not include any particle. So there are no particles released or emitted or absorbed. It's pure energy or gamma burst. So gamma particle happens most often after a alpha or a beta decay. The nucleus has gone through a lot and it's been jiggled so much that it needs to release energy somehow. It has to release this extra energy in the form of a gamma burst. So very powerful. So let's take a look at an example of a gamma decay. Let's use argon, an inert noble gas, 18 and 40. Argon is a gas that is used in if you have a double pane window or triple pane or whatever, how many layers of windows you have, they actually pump argon in between the panels of glass to provide extra insulation of inert air. Inert meaning it's not going to react with other particles around it. Argon is also found in light bulbs, in compact fluorescent light bulbs, not the Edison light bulb, as those are vacuum flasks. Okay, so argon undergoing a gamma decay, so gamma burst. So what happens is you have exactly the same argon, except the difference between this argon and the one that is released after the gamma burst is this is in the excited state. And argon after the gamma burst is now in the ground state. So this is a gamma radiation that is produced. So it is a very high energy, high frequency radiation, and it is used in medical physics and a lot of other technology that requires a lot of energy released. What is an excited state and a ground state? So in a nutshell, what happens is when particles move so much with such high kinetic energy. They're jiggling all the time. Atoms are always jiggling. But when they move from a ground state to a higher state, the energy is accumulated. So from the excited state, they move back down to the ground state when energy is released. Um, Without getting too much into photoelectric effect, so that's one thing that you could check out as well, is the photoelectric effect. This is what Einstein won the Nobel Prize for. So just on the side, this is Einstein's Nobel Prize. We don't have time to really go over photoelectric effect, but it is the basis of a lot of, probably all of the technology that we use today. And it is used in medical physics. So keep in mind that to summarize, we have in an alpha decay, you have the mass that seems to be missing from the release of an alpha nucleus, and it is really just the kinetic energy of the alpha particle and the daughter nucleus moving away from each other. And the missing mass in an alpha decay can be calculated using Einstein's equation E equals mc squared. In a beta positive decay or a positron, what happens is you have a decrease in the number of protons. So you go from, because a positive, beta positive is released, so a positive one. In a beta negative, what happens in a beta negative is that you start with a parent nucleus with a number, atomic number, and it increases because a beta negative is a negative one. Capture, electron capture, is basically a beta decay, but the opposite. It is absorbed instead of released. And a gamma decay has no particles released or absorbed. It's just bringing down the excited state of the particle into its ground state. And as a result of this, a gamma radiation is produced.